Today I will present some of the theoretical results that we worked on that are related to the talk that I gave a couple of months ago to the CIA seminar, if you were there. And it's a work done in collaboration with my supervisors, Helena Sledoni and Brin Polen, postdoc at NTNU, James Giacomo, and then Caroline Ferdia from the imaging group here. And I will present the work coming from two projects essentially, but first I want to set up a bit the notation and what is for us a neural network essentially, and in particular we deal with residual neural networks. So in general, neural network can be seen as a composition of some parametric function, and usually this parameterization has to be differentiable, so everything goes smoothly with gradient-based optimization method. And generally, the functions that we compose are all with a very nearby structure. So this is why I define them to be f theta 1 to f theta m. And if you look at the network as an input to output map, in the end, after training, so once you fix the parameters, this is just a function. And usually you want to solve a certain task, which is approximating a certain target function or trying to solve a PDE. There are many other applications. But in general, there's no constraint in the choice of these parametric functions, f theta 1 to f theta m, and one can play with it as preferred. And in the recent last 5 years or so, there has been quite a lot of interest in trying to put a bit more mathematical structure behind this choice, and essentially trying to borrow from the theory of dynamical systems and numerical methods for ODEs and PDEs to define in a bit more restricted way these parameterized functions f theta 1 to f theta m. So one way to arrive to this conclusion, this is not the only way, is to say that we have an underlying time interval, t0 to tm, generally 0, 1, that is quite arbitrary. There's no real time domain here in principle. And introduce a time discretization of it. So define a partition into subintervals of length delta pi. And on top of it, we can introduce a parametric system of ODEs. So this is the system of ODEs. One can also think to other physical models that works in the same way. And the important thing here is, of course, that there is the appearance of a parametric function, that is this theta of t. Because this theta of t is what lets the model be flexible, so you can use it to solve different tasks. And of course, the choice of f is important and depends on the task you're interested in solving. And then in an ideal world, we have the analytical solution of this, but in practice, this is not the case. So this is where these parameterized functions come into play again, because one needs to approximate the solution of this system of ODEs. And to do that, we need to use some numerical method. Any method you want, in principle, can be used here. And I will denote numerical methods or discrete flow maps with this psi, with a subscript, which is the vector field, fi, and superscript, which is a time step, delta pi. So this is essentially the vector field we get freezing in time our vector field at a specific time instant. And then your neural network is still a map from input to output space that is obtained as the time t flow map, or the approximation of the time t flow map of an ODE. Then this can be also embedded into more general settings that are more typical of modern neural networks that usually exploit the change of dimensionality of the input to make the function to approximate easier, less steep, for example, or more linear in many cases. So it's important to allow also for this variability in the dimension, while dynamical systems, of course, keep fixed this dimensionality. This is why we thought essentially to extend this by just limiting the dynamical understanding to some blocks of layers that we call dynamical blocks. And these are interleaved by some linear lifting or projecting layers that can be also in convolutional layers. So it's just a linear mapping. And also these dynamical systems can be involved in convolutional layers and anything you want, as long as you can define a smooth enough right-hand side of the ODE. So you can still get neural networks typical of image classification tasks or for solving PDEs, whatever you prefer essentially. And these FIs can be any numerical method again. So after this setup, I want just to present briefly the outline. And essentially the talk is divided into two parts. The first point is the first part, and it's about trying to develop some theoretical understanding of the approximation properties of some families of residual neural networks for the task of approximating data coming from space-time observations of special classes of PDEs. And then the second part of the talk is instead involving points 2 and 3. And here we essentially go in the direction of the field of numerical analysis called geometric numerical integration, which is a subset of numerical methods that is not just interested in quantitative approximation of the dynamics, but also preserving the qualitative properties of these dynamical systems. And I will just show how it's quite natural to reuse these ideas to structure neural networks and how one can try to still prove the approximation properties of these networks. So starting with the PDE part, and actually I want to say that here we are dealing with PDEs just because with PDE type data sets, it's possible to say something in terms of convergence because we know what kind of properties they have related to numerical analysis. But our main purpose was to understand what kind of families of neural networks, so very close to standard neural networks, we can use to model space-time observations of any sort in principle. And
yeah. So I think that was a bit from me. So you now in your network it looks like a PDE, or you try to approximate PDE with the
yeah, so this is the setup now. So we are trying to make predictions of coming from pixel-based data. So you have sequences of images or matrices, in particular in our case. And the matrices can come from a PDE, but even come from any observation that you have. In general, this is the setup. So now the purpose of the network would be to make predictions in time. So a sequential model that given a certain observation at time Tn, spits out the observation at time Tn plus delta T. Okay. So our data set in this case is a collection of n sequences of m time steps, of m snapshots, if you want, of a certain dynamical system or a certain temporal system. And this can be, in this case, I pictured, I used matrices, so two-dimensional data set. But in principle, you can use also higher order data set, higher order tensors in this case. So RGB images, for example. So the purpose is, given this sequence, try to understand what is a good approximation of the map that sends the observation at time Tn to the one at time Tn plus 1. So this is more or less the map we are trying to replicate. And just to show you an application that we work with, our project was mostly focused on the theory, let's say, and then we tried to apply these networks for which we were able to say something about the approximation properties to 3 PDEs that are, we use just linear advection heat equation and this nonlinear reaction diffusion equation, the Fisher's equation. So just to show you more or less the main point here is that we generate a data set, our data set, by randomly initializing the solution in n different ways. So in this case, they were all with this kind of trigonometric structure, but we had some random sampling that modified their amplitudes and their frequencies of these initial conditions. So we had some variability. And our data set consisted of 5 snapshots of this dynamical system, of this evolution of the PDE in space-time. And the purpose was to approximate the update map. So
So you took the initial conditions, you used the Fisher equation
To generate the data.
with a small time stepping numerical method, and that was the data.
Yeah, so we used finite element in space and with the quadratic
And then you try to learn
the update.
the solution.
Yeah. So this is very academic as a setting. In principle, this should come from some observation. So this should come from
And you use the time step larger than that was used for the following the Fisher equation, or it's the same?
no,
time
it's
step?
the same. The same.
Same,
It's just
okay.
that we.
So you know exactly what the map is.
Yeah, sure. This is why we wanted to test our theoretical setup in this case.
And you start with negative initial condition for the Fisher equation.
Yeah, it's both.
Negative
It's both up and positive and negative. So it's diffusing, but also with some source there, the reaction there.
Yeah.
Yeah, so our data set has 5 snapshots. So just 5 delta P's. But then these predictions are extrapolating at the same time. It's 40 delta P in this case.
Sorry.
Yeah.
So what uses a time stepping scheme? So you said it's some elements by.
So to generate the data, we use Graf-Nicholson in time and the quadratic finite element with quadrilateral element.
Okay.
Just
Okay,
quadrilateral, yeah.
So, okay, I think this is scheme. Okay.
Yeah. So we wanted not to have errors coming because of the data, but just because of the approximation that we were doing essentially. We wanted to isolate the problems. But and all the estimates I will present are based on the fact that we're supposed to have the data that are exact, so the analytical solution, let's say. But in principle, everything in our project we added to these terms the contribution coming from the measurement error. It's just for simplicity that I removed it here. Okay. So, and then again, as I said before, we focus on data sets that are not just random sequences or matrices, but they come from observations of a certain solution of a PDE. And in this case, what we suppose is that we deal with a two-dimensional spatial domain. So X and Y are the variables, and T is the time variable. And then we're supposed to have PDEs that have this kind of structure. So we have a linear differential operator L. So it's a non-stationary PDE, of course, with a differential operator L. And then there are non-linear interactions between the derivatives of U. So alpha ij are multi-indices that take the partial derivatives. But in principle, this can also be just U. So it's just a general notation to describe this kind of structure. And then what we have is that there is, since we want to deal with matrices in our case, we're supposed to have these solutions sampled on a uniform grid. That can be done, for example, generating the data set with finite elements, but also just observing with some sensors, ideally, the solution. So this is the grid, and the matrix that defines our data set is just the sampling of the solution at this grid point. So this is essentially what I meant before with our sequence of matrices. Each matrix is just the evaluation of the solution, a specific time and space location. So the main idea behind everything I will show is very simple, and it's related to the dynamical system interpretation of residual neural networks we have seen before. And there is a very similar idea also in classical numerical methods for PDEs and non-stationary PDEs, which is the one of separating the time, the discretization of the spatial derivatives and the one of the integration in time. So this is the method of lines. I don't know if probably there are other names for it, but this is the original PDE. Then the first step of this approach consists into getting a semi-discretization of the PDE and turning it into an ODE. And this can be done in many ways with finite elements, or in this case, we will use finite differences as guiding principle. because this makes a very easy connection with convolutional neural networks. And then you can just use any numerical method in time that you like. Of course, it's not that great because you need some stability analysis and so on, but this is just for the sake of presentation here. What you can do is, after you get this semi-discretized ODE, you can integrate it in time. So this is again what I use as a notation. This psi of f delta t is just the example of explicit Euler because it's compact. And our u of t is just the approximation that with some quantifiable error in this case can be, for example, big O of delta x squared and second order finite differences, for example. And it's the approximation of our scalar valued solution. Yeah,
but now delta t is probably much smaller than delta t before.
Why?
I mean, it's now, it's the explicit scheme for.
Yeah, but
probably it's like Lassian, I guess.
No, sure. This delta t, this is not the method we use to generate the data. This is just
So that's what you use here now to construct your neural network.
Yeah, in the end, yes.
So then I would guess that it needs to be much smaller than before. Or,
Yeah, so
it was very small before. That's probably
exactly. But so this is very consistent with the stability barriers of explicit method. So we have the CFI condition essentially that get into play. And but we didn't want to use implicit methods because even if they are very but because of the size of the data set essentially, and also because our purpose was to prove that commonly used neural networks can approximate this kind of data. And commonly used data neural networks are usually very related to unexplicit order discretizations that of a certain right-hand side, which is a parametric function.
I guess we have no idea what these people are doing, right? I mean, they can be horrendous.
Yeah.
Okay, right. I mean, all
Sure.
these partial derivatives and higher order problems.
Yeah.
It's just a huge mess, right?
We stopped actually to quadratic interaction in practice. So am I question.
But if you think about neural networks, you also have to have some integral terms there. I mean, I can see the differentiation why you want to have that in there. But well, I don't know, maybe it's
What do you mean?
kind of like normal weights times kind of more like a convolution. I mean, not like a convolution, but that's not complicated. But it's oh yes, exactly.
No, I don't know exactly
Yeah,
what you were asking.
By the differences, that's one kind of convolution.
Yeah.
But you can have other ones. That's
Yeah.
what I'm thinking about.
Sure, but okay, I get your point. I will try to get back to it later. So what I wrote here, this star operator is, as you probably have seen, understood, this convolution. But because any convolution, any finite difference discretization up to order 2 can be well represented by a 3x3 kernel, actually. So you can always represent, instead of using a Toeplitz matrix and you vectorize, you can still keep U as a matrix and just apply a convolutional filter on the left of it, which is what is done for edge detection, for example, in images and so on. So this is essentially the main thing I want to say here, because you can always represent this, for example, for the Laplacian, you can use the 5-point formula, center point of interest. And you can represent it with a 3x3 filter that of course depends on the grid, and it allows you to get the same delta x squared error that you would get with classical without dealing with convolution. So I'm not sure if everyone is familiar with convolutions, probably yes, but just to have a bit of explanation here, convolution is a quite simple linear operation that is behind the success of many image-based neural networks. And essentially, it can be represented as a dot product of a certain filter, that is K in our case, that is a 3x3 filter in this case, with some windows, some blocks of contiguous matrices inside our input. So, and usually what you do is to add some entries around the input. So you pad the image or the matrix. And this is exactly what is done also for PDE discretizations. Depending on the boundary conditions, you choose how to pad these inputs. And this is the example of a periodic padding. And you just add a boundary essentially, one row and one column on each side. And then you slide your convolutional filter K around the matrix in all the possible positions, and you compute this dot product. This is just the first entry of the output. And an example is this filter that allows you to get convolutional filters that represent finite difference stencil. So now let's go back to our approximation problem. And what we worked on is essentially a relatively natural error splitting in this setting, which is very close to what is done usually to measure the local error in space and time of method of lines based on some discretization method. So what we want to do is essentially supposed to be in the exact position, UN. So UN is a matrix now. And we want just to do one step in space, in time, sorry, and see how far we get from the truth. This will allow us to account both for the spatial error, because we know that this f of theta, or this f that we are working with, is a spatial discretization of the right PDE. But then we also, it also allows us to account for the time error, because we are using a time stepping scheme. And now what I want to do is actually not to directly supposed to know the correct vector field f, because this is the main point, but I want to see how far I would get from the truth, or I could get from the truth, using a certain parametric function f of theta. So now, for simplicity, we can think just to a one-layer residual neural network. So it's very simple, but this can be made as complicated as you want, as long as you can reconduce this to a certain numerical method for which you know the accuracy. So you can also think to do, let's say, L substeps of this numerical method, all of length delta T over L. This is another simple thing to do. And it's still a ResNet with just different weights and so on. But this is just any numerical method, and what I use here is that it's a method of order R, so that the local error is delta T R plus 1. So the main point here is just to start with that estimate, that quantity that we want to estimate. And then, since it's easier to work with exact flows, so this phi of f delta T is the exact solution map in time of the vector field f. And what we do is first recall the fact that the analytical solution UN plus 1 is not exactly coinciding with this exact flow of the discrete ODE, because there is a discretization in space. So this is this O delta x squared appearing, and this the spatial error. We cannot do anything about that. It depends on data one has to deal with, essentially. And then what we have is essentially a splitting of the error in meaningful parts. One is classical error estimate, in the sense that we just account for the error made by the numerical method we use in time. So this is something we can play with. We can increase the R depending on the choice. Of course, the cost also increases. And then there is another part, which is what we focus a bit more on, which is the neural network approximation. Because the main thing here is that, of course, we don't know F. So this is the main purpose, that we would like to get out of this estimate a way to measure how bad we are doing in time, let's say, as a sequence mapping, based on how bad we are doing in space. So how bad is the approximation of f theta provided with respect to f? So what we do is essentially just to transform the problem from discrete flow maps to exact flow maps here. And this is just using the fact that this is a matter of order r+1. So there is a term absorbed here. So it's simple, just translating to exact solution maps here. And then as usually done with approximation theorems in this kind of field, we always try to work on compact sets. So that in particular here, even if we have polynomial interactions between the components, we can still bound the Lipschitz constant, and we can use a Grunwald type result to get an estimate of everything related to essentially how bad f theta is doing in approximating f. So this is exactly the term I want to study now. And what I want to do is relatively simple. It's based on just these two activation functions and the fact that we can always represent finite differences with convolution. So it's no more than mixing these two things. And the only not so common thing we are doing here is that we will obtain a neural network that has two activation functions instead of one. So it's processing the inputs differently based on what kind of it's not using always the same activation function essentially.
So the activation function is done between kind of two steps of this PDE with the nonlinear part.
So the neural network we will use just to go to something more concrete. It's just a single layer neural network. Okay. So you first have a linear convolutional layer that processes your matrix, which is the approximate solution evaluated in space at a fixed time. So this is the input of your network. Then what you get, so this is a way to prove the result, but first we don't know if in practice the network test is. But what we do is that the first convolutional layer will generate all the derivatives you need, essentially. And then the activation function sigma, which is based on the two I am presenting now, allows you to combine them properly, so that in the end you can exactly represent the vector field that is the right-hand side of the semi-discretized PDE, as we have seen before.
What do you mean by, you mean that you expect that in the classical neural network that can be obtained from the optimization, you will have this one.
Yeah, exactly. Yeah, so this is a lot weaker than classical convergent theory. Yeah, it's more like universal approximation theory.
Yeah,
kind of.
Absolutely. Yeah, and the question is, we know if this one is the one that is actually one.
Sure. So the main point here is to use two activation functions that are relatively common in the literature, and one is the ReLU, which is a lot more common than the right-hand side. And then in some papers recently, many people have tried to take powers of this ReLU function, and in particular the ReLU squared, with this one. And the reason why we were looking for this is essentially to get back to what we know how to deal with our polynomials. And in this case, the very nice property here is that you essentially can obtain any power of x just by properly combining these two activation functions. And since we just focus in our theoretical result on quadratic interactions, we just need power 2, essentially. This is the main idea. So just for the sake of the presentation, I decided to focus on this right-hand side, but this can be made more complicated by linearly combined terms of the second part, as we have seen before. And so the purpose now is to see if a certain family of parametrized functions can represent exactly this right-hand side. Of course, I'm sure that you are thinking that why do you need a neural network here? Yeah, I agree in that sense, since in principle, we just need three matrices, right? L, V1, V2. And this is a lot better in practice. You get machine accuracy in the approximation. But our main problem of interest was to define a class of parametric functions that is still able to approximate this kind of right-hand side, but without being just restricted to that, because this is not what we have done at the moment, but this is the direction we want to take. This kind of networks, ideally for us, would be of use to approximate any other sequence type data set, also not coming from PDEs. But since PDEs are covering quite a huge family of models, we wanted to be sure that at least those families were included in this proxy space, in this approximation space. So these are the two main ingredients that are essentially just an extension, distinction of what we have here. So we just recover the identity map with sigma 1, just sigma 1a minus sigma 1a minus a, sorry. Yeah, otherwise it's quite trivial now, even more than this. And the other one is just recovering the product of two numbers. And since all these activations functions in neural networks are applied entry-wise, you can do the same also for matrices, and everything works still. So this is just combining properly the activation function and linear maps. This is the main ingredient here. And you can see that to capture a quadratic interaction, we need 6 terms. And to capture a linear interaction or a linear term, 2 terms. So this is the main reason why on this picture here that represents our neural network, we will have 6 phases of our output tensors or our tensors in the hidden layers that are aimed, these green ones, that are aimed to capture the quadratic interactions. And then the blue ones are aimed to capture the linear part of the PDE of the right-hand side. So the first linear layer is simply trying to extract the meaningful information from our image, our matrix, that relates to all the derivatives we need, more or less. And then the sigma part is essentially trying to combine, we just apply the nonlinear function to all the matrices. And then what we have seen here is that we can recover the L times U part by simply summing or subtracting the first part, sigma 1a, with sigma 1 of minus a. This means that B star U is simply taking the difference of the last two phases of the tensor. While for this part, we need a bit more, in the sense that we need to take 1/2 of these 2 parts and minus 1/2 of these parts and just sum them up. But this is something we can easily do with convolution. So this is essentially the main idea, and this allows to prove with a very constructive and simple argument, let's say, that as long as you have this kind of functions, parametric functions in your approximation space, you are guaranteed that you can, at least theoretically, exactly represent this family of vector fields. Then, of course, in practice, this never happens using these kind of networks, because you have the optimization error, and everything depends also on the quality of the data that you have to practice. But yeah, this was the main purpose of our project, essentially to try to understand what kind of families of networks that are close to the standard ones can naturally represent this kind of right-hand sides of the PDE. So this is quite different than physics-informed neural networks that try to solve the PDE in a non-supervised way, essentially. But it was trying to use space-time discretization ideas to show some approximation properties of the model. So yeah, if you have questions, then I switch to another part.
What I didn't get, you said that your F theta, your F is basically one a specific F theta,
Yeah, yeah.
but this F corresponds to, it doesn't correspond to discrete time. The
Yeah,
discrete
so-
expression, or is it?
Yeah,
It is already.
yeah, so actually what we have, this is just the
Okay, so
previous
we-
line, we just have the last line, right?
Oh, yeah, okay, so it means that your error, your first error is for the discrete one.
Yeah,
It's just
exactly.
the time discrete.
Yeah.
You know.
But
But you are not analyzing the full.
No, UN is the exact solution. UN plus one, sorry. UN plus one, and this is why here, once we go back
Okay,
to the exact
special
solution,
error is the first
we
case,
add the special error.
so that you can have the F which corresponds already to the final difference.
Yeah, exactly. So we can compare our convolutional based network with the finite difference.
The constant in your first special error shouldn't be dependent of delta T.
Like the space, isn't it a space?
Yeah, it's
distribution?
like,
So
okay.
you start from here.
No. Just like when you do the full numerical analysis, you have to be careful in the way that you are doing the triangular inequality, so that basically the constant that you have in your each term of the triangular inequality does not depend on the discretization parameter, other discretization parameter. But you can be sure
Okay.
that sometimes when you do the triangular inequality, like two quick things, sometimes you did like the first one depends on H, whereas the second one depends on delta T. So
Okay.
basically when you go to zero,
You do this.
the constant can be explode. But I'm sure you
Okay.
have it before.
Yeah.
I was just trying to do it by hand.
Yeah, no, okay. Yeah, okay, I will think about that later.
Okay, sorry.
So what I'm wondering, I mean, you kind of construct this neural balance correctly, you can with the PDE itself. Yeah, so I mean, as you said, it's not lines, and they kind of
Yeah.
but you still use an activation in between, but it's not essentially part of the PDE.
Yeah.
But could you also, and I mean, again, I'll later tell you this, I cannot really way to do that. But did you also think about a PDE that may contain something like a threshold in, like activation function?
Okay, yeah, that is something which is, there are papers doing it, I think, but it's, at least all the works I've seen, use the problem of interest is the opposite way around. So using PDE with this kind of nonlinearities that are typical of neural networks to motivate the architecture of a certain convolutional neural network.
Yeah, okay.
There are many works like Renko do it. And Owen. But I don't know if this is what you were.
No, I think I'm making it this way now. They're gonna say, okay, you start with your network and then you have a kind of PDE. Yeah, you also look like a say convolutional network by altering activation which things. So I can tell you later more.
Okay, yeah.
That's not.
I don't know, okay. Good, so now I want to present another possible ways that we worked on to use theory from numerical methods and geometric numerical integration in particular to define neural networks that have a prescribed property. So they have a certain structure regardless the optimization method. So even if you don't solve very well a certain task, you are still guaranteed to have the property. And these are just three applications where it can be of interest. It's still toy examples, of course, but the main point is that I think can be seen here. And for example, if you want to approximate that, as we have seen before, some sequence based on some underlying physical process, as usually done with numerical methods, it might be relevant to preserve the structure. This is, for example, what you want to do in population dynamics when you want, for example, to preserve that the sum of the state, the components of the state vector is always one at any time instant. like the SEER model, for example. Or you might want to approximate the dynamics of a certain mechanical system that is constrained to a nonlinear manifold. And if you want to do it in a data-driven way, it might be relevant to preserve the structure also in the modeling part. And this was actually the starting point of the previous project that then we left because we decided to focus on a different problem. And in this case, we still have a linear transport equation, but the data set is characterized by a low rank object, is a rank 2 at any time. So we wanted to create networks that exploit this low rank structure. And in particular, also make them more efficient in the computation, but we are still working on that, or we will work on that. But this is more or less another application in which it might be relevant to have structure preservation of your network. So there are many works doing something similar, but all in an isolated way, in the sense that there are many situations, again, when a specific property is of interest. And in that case, people reasonably constructed architectures that satisfy that property. What we wanted to look for is a method that at least gives you the possibility to impose in the same way or with the same procedure more than one property. And in particular, we deal with properties that are closed under composition, like being volume preserving in this case, being symplectic, being energy preserving, or being on a manifold, for example, in the case we have seen before. And the main procedure is based on 3 steps, usually. And the first one is, of course, deciding the property you want. And just to have an example here, I will go through the case of volume preservation. Then what we need to do is to introduce a family of vector fields that will be used afterwards to define your neural network layers based on this idea of discretizing the solutions of these vector fields to define the network at the top. And the main thing we want here is not that the vector field satisfies something, but that the integral curves, the solutions of these vector fields satisfy the property T. And an example for volume preservation is, of course, any divergence-free vector field, but a relatively simple and also effective parameterization of them is this partition vector field. So we want still to have flexibility, so you need as many parameters as you need for a specific application. And in this case, we can model using a relatively standard neural network this divergence-free vector field using this partitioning of the state vector into X and B, or 2 parts. And this is divergence-free by construction. So you can define your family of vector fields in this way by letting A, B, and small d be arbitrary. And this is your approximation space. Then the problem is that when you discretize them, of course, it's not guaranteed that you can preserve this property on the solutions, and this is the main point of geometric numerical methods. So you need to choose some numerical discretization method that allows you to preserve the property also in a discrete setting. And just as an example, again, going through this volume preservation, you can make a bit, use a method that is slightly more complicated than explicit order, but it's just 2 explicit order steps. So we can split this right-hand side into 2 vector fields, where one of the 2 halves is set to 0, and then just use the Lee-Trotter splitting method. So we do 1 step with the first part here, and then with the changed version of the first half, xn plus 1, we do another step of the second part. So this is volume preserving because it's a composition of exact flow maps of volume preserving vector fields. So these are all maps that we can then compose one with the other to generate our neural network that overall will still be volume preserving. So other 2 examples can be the one of mass preservation, which is the one we used to define, to get the example we have seen before for population dynamics, let's say. And in this case, any mass preserving vector field can be written in the form of at the top. So it's a skew-symmetric matrix valued function multiplied by the unit vector one there. And because being mass preserving means that you have a conserved energy which is linear, and this I of x, which is the sum of the components. And the Lie derivative, this gradient against the vector field is 0 in this case. And what we did is to model the skew-symmetric matrix values function by this the reshaping of a certain vector value neural network, which is this one here. I set n squared here in terms of entries just for simplicity, but of course you can just model the upper triangular part and everything. It's more efficient. And then another family of networks which is very popular in the last 3 or 4 years is the one of Hamiltonian or symplectic neural networks, especially for data-driven modeling. They have been used quite a lot. And many of them can be reconduced to a specific discretization of a certain parameterized Hamiltonian vector field. So you will have a neural network which is scalar valued, essentially this energy H, and then you can define your vector field just by taking the gradient. But yeah, I'm sure you're very familiar with this. And then just to go through these examples again, you can use any Runge-Kutta method, but actually any linear method, and you still preserve this linear conserved energy. This is just a simple proof for an explicit Euler, but it extends to any linear method. So you can use whatever you want, and this is well preserved, and you get a mass preserved neural network. And similarly, you can use any symplectic method, and you get a symplectic neural network. So nothing particularly strange. The main thing that comes out, at least that we were thinking about, is that of course it's very nice that you can impose some structure on the network, but you get very constrained neural networks in some way. So you lose in principle, you lose the approximation properties of your unconstrained network. So we were looking for some ways that one can try to prove that you can still approximate sufficiently large families of functions. And this is one of the results we thought about. And it's essentially relying on the fact that in many other works, it has been proven that you can approximate a continuous function by composing flow maps of C1 vector fields, also smoother than C1. So there are many works about that. So up to any accuracy that you want, this is still in the principle of universal approximation theorems you were saying before. And once you can do this, you can also prove that you can approximate the same function with the same accuracy, but with more structured vector fields, in particular, in this case, gradient flows and sphere preserving vector fields. So vector fields that have a conserved energy, which is the norm of x squared. So they are all orthogonal to x at any position. And the main idea behind this proof is the proof of this theorem is essentially that you can split any C1 vector field into the sum of a gradient and a sphere preserving part. And this is a global decomposition, so it's on Rn. And this allows you to rely on the theory of splitting methods, or the Becker-Alford formula, essentially, to just approximate the flow map. This is just the intuition, but you can add the details here, and you can prove that any function f can still be approximated by composing flow maps of this kind of more structured vector field. So what I would like to get, and I still don't know how, is essentially remove the sphere preserving part and restrict the family of target functions to not being just continuous, but being, for example, Lipschitz with some constraint on the Lipschitz constant. And this is mainly because of the fact that we use this kind of only gradient-based networks for some applications. And I would like to understand if there is some guarantee behind that. But yeah, if you have any advice, it would be great, but at the moment I have no idea how to do it. And I don't know how much time I have.
30 seconds.
Yeah, so this is the last slide.
If he says.
No, this is the last slide, but if I have more time, I can show you just the one application, but
Maybe
otherwise,
let's show us one application.
yeah. So maybe not, this we have already seen, not the survey, so. The application of that we used, in which we used the gradient flow based neural networks is the one of adversarial robustness. So we were trying to make neural networks less sensitive to perturbations in the input space. While, for example, state-of-the-art neural networks that are super accurate, even with this is C410 data set, are very sensitive. So this is classified with 99% certainty as a plane, and you have this perturbation in the edge norm that for us is unperceivable, and the network will classify it as a cat with the same kind of certainty. So this is not a reliable prediction, of course. So there has been quite a lot of work in trying. You never know, but maybe behind there is a cat. So there has been quite a lot of effort in trying to show that at least in some way you can improve the robustness. And the main idea has been to work with the Lipschitz constant of the neural network and constrain it so that you can improve the sensitivity. So what we did was to create a neural network that is based on the dynamical blocks that we have seen at the beginning. So you still allow for linear lifting and projection layers, but these dynamical blocks are based on alternating these contractive and expansive flow maps that are both based on the gradient of a certain function, which is quite typical in neural network literature. So it's essentially composing flow maps of this x theta I vector field, which is the minus sign applied to a gradient of v theta, and we took sigma so that this is actually strongly, this is the gradient of a strongly convex function. So you can ensure that this is dissipating or contracting.
So sigma is the sigma function, or is it one? I mean,
Yeah,
sigma is
so-
a matrix, or is it a function?
No, actually, sorry, yeah, it's a function. Just the negative implication. So sigma of x is max. So it's just this. And sigma is essentially the sigma of V1. It's just the component wise application. So, and the reason why we did this is so that the integral of this is strongly convex. The integral of this, so this is the gradient of a strongly convex function, and you can use one-sided Lipschitz inequality to prove the contractility of the dynamics. But that kind of approach limits a bit the expressivity in practice of the network. We don't know in theory if this is the case, and this is what I would like to do. So this is why we allow us for expansive layers here. And but overall, we still want to have a contractive behavior. This is why we are studying the expansivity of these two maps. And the main thing we do in practice is to constrain the time steps of pairs of these flow maps so that overall they stay contract. Even if you allow for an expansive step, you will have to have a longer contractive step essentially afterwards, so that the combination is still contractive or non-expansive. So the network is this alternation of contractive non-expansive layers, but overall you still can ensure that it's one Lipschitz, this network essentially. The one is just a choice, but you can just rescale everything with linear layers. And if you can, the main point here is that being one Lipschitz allows you to be easily setting a specific Lipschitz constant on your network afterwards. And this is just the conclusion essentially. So we used various ways to alternate these steps, these expansive and contractive steps. And we, this is what I call switching prescribed and switching flexible. And then unconstrained is the one I used to generate the cat example before. So you see that if you increase the epsilon, sorry, yeah, the epsilon is the magnitude of the perturbation to the image. And on the y-axis, you have the accuracy of the model. This is actually for a more complicated data set, so it's CFAR 100. This is why we have relatively low accuracy of 60% at most. But this is the standard if you don't use very huge networks. But the main thing here is that it decreases somehow linearly instead of exponentially. And this is the main consequence of having a constraint on the Lipschitz constant and also some adjustment in the optimization. But this is the main thing, essentially. And these are just
really so good. I mean, like, if you have a Lipschitz constant, I mean, like, if everything gets mapped to the same point, right?
Sure, yeah. In the end, you can.
Beautiful Lipschitz constant, right? But it doesn't give you much, right?
No, this is why I said that there is some trick in the optimization. So it's a trade-off between being zero Lipschitz and also being able to separate enough the classes. So this is the margin. And so in the output space, you want your classes to be well separated. And it's not really the Lipschitz constant that matters, but it's the balance between the margin and this Lipschitz constant. Otherwise, yeah, a constant function is perfect. It would be a flat curve at 10%. No, 1% here. So yeah, this is everything, and thank you for the attention.
All right, so we'll have time to think about lunch. Oh, you have a question? Oh, yeah, more questions. Okay, so
You get more time.
yes, thank you. Yes, I haven't decided yet.
Like, let me think. So basically, yeah, how many? What I didn't completely get is that how many? What do you optimize exactly when you? Do you optimize the link between U and +1 and C?
Okay, yeah.
To find the theta, and what size is the theta? At the end.
What size?
Yeah. So basically, how many?
How large it is?
Yeah.
How large? How many parameters we have?
Yeah.
Okay. Yeah, this is the main point. So yeah, the first thing you say is correct. So this quantity that we measure here is exactly the term that you have in the loss function.
Okay, so basically, why don't you just say here that typically this error, since you optimize on this error, should be controlled by any type of theta. So I don't get why you don't go one step further in your proof, saying that, okay, since you want this to be the smaller as possible, it's what your neural network, your optimization process do. So assuming that the neural the optimization process has converged, so yeah, the only problem then is that okay, that's maybe what you want.
No.
So if it converges, then at least you will have some kind of error for any f theta.
Yeah, for any
your error is smaller than any for any f theta. And you find one that actually where actually basically everything is on the first two part and nothing on the last one. So any other should be even if
if you let theta be any, let's say, then this is not yeah, of course this is a bound that still holds, but this can be a very large quantity, right? If theta is not the proper one or a good enough one.
Yeah, but you know that the one that works will be better than any of them.
Sure.
So in particular, the one that you choose And for the one that you choose, the third term is zero. You look at which statistic change anyway, and so basically all zero are in the two others. But I don't get.
Yeah, so the two others, if this is zero, then this means that essentially we are doing a consistent discretization of your correct PDE.
Okay,
There's no, yeah.
And so what is the sign of people?
Yeah,
Then
so-
what I would expect is that the final word of your presentation should be okay, and in practice, theta is much less.
Yeah, it's actually the opposite.
Like it's bigger than what you get from,
Yeah, this is what.
bigger than what you get from finding difference.
Yeah, so what we, yeah, exactly. And this is why I was saying before that, of course, this is the best thing to do, to replace the three matrices and just optimize for the three matrices.
Yeah, but then you get something which is much more.
Yeah, if you just do this, yeah, for sure. If you don't use a neural network and you just introduce a parametric model, which is just having the unknowns LD1, D2, then the optimization problem is a lot easier and you get better results. But if you involve them in a network of this kind, that in principle is able to represent that, but in practice, it's not what is doing, essentially. Then you need to embed this network into a larger one. So you need to allow for more phases in this.
Yeah, but at the end of your optimization process, do you find some kind of sparsity in the parameters that you get?
No. You get them, of course, if you regularize, if you add some structure on the parameters, but you don't get it if there's nothing imposed. It's not learned.
So basically, if I summarize, you say, I know how to cook something, so I put more ingredients in it. Since the ingredients that I put in it correspond to the ingredients that correspond to the recipe.
Yeah.
I may find
Yeah, this is it seems very down here, and it is in the sense that it's not the most efficient way to do it. And you need more parameters. But this is because we know that the right hand side here is like this, because we know the structure. And this allows us also to say that it's not the best thing to do for that reason. But if you don't know that there is a PDE behind, you cannot impose some structure. The filters. Yeah, so I totally get the point.
And my last question is that if you perturb the input part
with noise or anything,
can you also find a very different P? And you expect to find a very different
the network
P structure, basically.
Yeah, so of course there's no
That
yeah. So the quality of the data, of course, affects the estimates in the sense that you can just account for that measurement and essentially you have an additional term here because you cannot deal with noisy data, or you can, but you get an output which is as good as the but yeah, it is more robust that you would get than what you would get using this, just replacing the three matrices. Because in the end, you can still represent a huge larger family of functions. When here, this is trying to fit something that is driving away from the truth.
Okay, well, that could be a way to justify that actually. Sure, it's better. Than so everything is in consistent.
Yeah. Right.
All right. Okay. Any other questions? All right. Thank you.